Alright, I guess you are all running through busy schedules and not finding time to cope up. Is that the case or?
Yeah, yes, sir, kind of.
Okay. Alright, in the last session, I guess most of you had a lot of difficulties in understanding what processes are and how do they communicate. One of the IPC that I showed you was pipe. So let's see in great detail what really is happening behind the scene when a process creates a pipe. Now pipe is a IPC to communicate between two processes which are related. It means there should be a parent-child relationship or parent-grandchild relationship like that. So for simplicity, I have taken a parent process which will give rise to a child process using fork. And when you create a pipe here, actually what happens is in the kernel space, the pipe data structure will be created. Okay, it's a kind of two-way communication channel. It means you can write to it or also read from it, from both the ends. Here also you can read from it or write to it. So since only parents want to write something to it, I will keep the write end open here and close the read end. Similarly, here I only want to read. Keep the read end open and close the write end. So that one-way communication happens between the child and the parent or the parent and the child. So this is a scenario of the parent-child relationship, and if they at all they want to communicate, this is how they have to do. Because the process space of parent will be different from process space of child. You will not have any common memory area where they can put their data and communicate. Okay, so this is one of the IPCs. We shall see three more: shared memory, message queue, and all. So, looking at what we did last time, the interprocess communication, if it has to happen through pipe, you have to have related processes. So let's look at that once again so that you have a lot of clarity in what we are trying to do. So I have a sample code here. So you require some header files like unistd.h is required for most of the functions, like you want to define the process descriptor PID, then this unistd is required. And if the parent wants to wait for the child to complete, you require this wait.h, and string is required because you want to write something into the pipe and read it into the buffer space. So last time we saw how to create a pipe. You just have to say pipe fd, and you normally whenever you do a system call, always check whether it returns -1. If it is returning -1, there is some potential problem, so you must report that. Printf error creating pipe. So
So at what cases the receiver can be -1?
pardon? Only when there is a problem, that it is this pipe system call fails. This may be due to many reasons, that you might have run out of memory, or there might be some system error or something. So this will return -1.
Okay.
Okay. So if it all returns anything not equal to -1, maybe 0 for successful completion, then you will be out of this if block. Okay. So after creating the pipe, you just have to create a child process by calling fork. So fork will return twice, once when PID is equal to 0. Now you might as well ask, this fork will it return -1? Yes, it does if it fails. So there again you should have a if block like this. If PID assigned to this equal to -1, here you can say again printf error forking. So this is always a good practice to include these kind of if statements, so that you are pretty sure that these system calls have not failed. So if it is not equal to -1, it means fork has executed correctly, and it will return twice in the same program. First time it will return with a value 0. This is the child process space. Remember this. So how do I distinguish between the child process space and the parent process space? If whenever the return value is 0, it means you are into child process space, and if it is greater than 0, then it will be parent process space. Just 1 minute. Yeah. So what is that I have to do in the parent process space? A parent process space can write a message to the child. So you can take a string like good afternoon. So it should be in just double quotes. So this is the message the parent wants to send to the child. Now since you don't require the right end, you can close it. So if whenever you create a pipe, it will return two values, fd0 and fd1. fd1 will be right end, sorry, fd0 is read end, so it should be closed, and fd1 is right end. So here you can use right fd1, and the message that you want to send, and this should be string length of message +1, because the length will be 1 less, so you should add 1 to it, so total length. Yeah, so this is what the parent does, and if it wants to wait for the child, you can call wait here with null value. It means it's wait for any other process related to it, and after completion you can give a printf I waited for the child to complete. Okay, so this is what the parent does. It will close the read end. Remember, fd0 is the read end and fd1 is the write end. So this is the read end closed by parent. Now exactly the opposite should happen here. You should close the right end here. So close fd1, and you want to read, should use fd0, and you want to read it in the buffer which I have declared here of 100 bytes. If you want, you can make it slightly larger, and here you can use size of buffer, and whatever you have received you can print it here. Printf I received message from parent %s /n, and here you can print then whatever it has come in the buffer. Okay, so the child need not have to wait for anything, it just can close. Okay, so when it reaches the end of the if block, the child has completed. Okay, it will come to this return 0 here, and the program ends. Is it an extra bracket here, or I think so there is extra bracket. Let me check once again. So you are declaring a file descriptors 0 and 1 for read and write, and you are taking a PID variable to keep track of the process ID, and you require a local variable buffer which will receive the string sent by the parent. So first you create the pipe. If it fails, you report it. If it goes successfully, you create the child process. Again, while creating a child process, check whether it goes through successfully. If yes, check in the parent what message you want to send, then close the read end. To the right end, you write the message and wait till the child completes, and in the child you close the right end and read from the read end and print the message. Okay, so this is a complete program that we saw last time. To run this, I have to save gcc pipe1.c -o pipe1./pipe1. So as you can see, I received message from parent, good afternoon all, and the parent will come back later saying I waited for the child to complete. Okay, so what was sent by the parent process is captured by the child and it is displaying it here. Okay, is this concept fully clear now?
Yes, sir.
Okay, I will share this code. I think so I have done this, but you also try at some leisure time how this whole thing works, because understanding processes and the inter-process communication is important. Okay, now we saw how two related processes can communicate. What if the two processes are not related? That is a scenario. Okay, so as you can see here, the process 1 and process 2, they are not parent child. This is a complete different program, which is a process. This is another process which is initiated by another program. If at all you want to communicate using two processes which are unrelated, then you can use message queues. Okay, so again, message queue is a kernel space data structure where you write from one end and read from another end, and always you can send any number of messages and each message will be designated by a type. So message type 1 may be all personal messages, message type 2 may be like all professional messages. So we can designate like that, and in the demonstrative program I'll show you how to do that. So as you can see here, the processes here are totally unrelated, and to send the data to the message queue I am not using write here, I am using message send, msg snd, and to receive the data I am using message receive. Okay, so two unrelated processes can communicate using the message queue. So let's see how all that is done. Yeah, so you require two processes, means there should be two separate programs. So message queue send is a sender process, message queue receive is another process, which are two different programs. So let's see what we are doing in message queue sender program. Now any message that you want to send should have two parts. One is the message ID, which is a long data type or the message type, and second is the actual message. You can take any length. I have just taken 264, it can be 500 also. So you have to declare a structure like this. That's the first part of it, and it should include a header file msd.h. Now how do I create a message queue? The way to create message queue is using message get system call. Now every message queue should be uniquely identified, and this should be known to other processes. So I am just using a fixed value here, 1 2 3 4. You are free to choose any value. So the receiver, if at all wants to get messages from this, it should use the same number which I am using in message get. So the receiver will also use a message get, but it will not create it. It will only execute message queue without this IPC create. Now this being a sender, it has to create it because message queue does not exist. So there is a constant called as message create or IPC create, and this 066 indicate that the owner, you only as a user, has read write permission. Group members also have read write permission, and others also have read write permission. So 666 indicate that everybody has read write. Since message queues are meant for sending receiving messages, both read write are provided. Now you declare a variable of this structure, that is struct message msg, and this being a sender, you first print a message, I am sender message queue, so that you know which process is what. And message queue type or message type can be different numbers, 3 2 1 like that. So I will designate the personal message as message type 3. So type 3 message, personal message, hi Ajay, how are you, like this. And the way to send this message is whatever QID, the message QID which is returned by message get, it is an integer which will help you identify the exact message queue that this process has created, and the same should be used while sending and receiving. So msg send QID, then address of the message, the whole structure, and size of the text part of it. So don't take the size of the entire message structure, only the text part of it. And here last argument is 0 because there are different options like wait, no wait. After you have written the message, you don't want to wait, you just want to proceed. So it should be 0 here. Otherwise there will be one constant like IPC wait. So this will wait until the message is read. Okay, so you can use that constant, otherwise you just put 0. I am using 0 because I want to write one more message. So message type 2, this will be a professional message like Ajay, you are promoted as tech lead from Feb 2026, like something. And I am sending the same message queue, another message, and the type of that message is 2. Now these type numbers will be helpful in the receiver. If I want to receive personal message, there I should use type as 3. If I want to receive professional message, type as 2. We'll see that happening, and then the size of the text that you are sending as before, and again 0 here. So this is what is the sender process will do. Okay. On the other hand, if you look at the receiver process, the receiver process again has the same structure, message type, and text size is same. Here I am again using message get, but observe that I am not using IPC create here because that is already created by the sender. I am just using it, and the ID has to be same. There I used unique message queue ID as 1 2 3 4. Same I am using, so that the existing message queue will be referenced and you get the message queue ID as the integer. And the message that you want to receive will be again in the same message structure, MSG. So here you have to decide what message you want to receive. Let's say I want to receive professional message. In that case, message receive QID, address of the message structure, size of the message text, and here for personal we have seen it is 3, and for professional it is 2. So I am putting 2 here. Here again it is wait, no wait. So I am just not waiting, I am just proceeding. And whatever message that I get, I say received message type 2 and displaying that message. Okay, so let's see whether these two programs go through. First thing is I have to compile these. Message queue underscore es.c minus o. we can say sender. Similarly, receiver. Okay, first the sender has to run. So it has sent, it only says I am sender message queue. It has sent already. Now only thing is when I run the receiver, I have to see whether you get the correct message. Okay, so it says type 2 message, professional message. Ajay, you are promoted as tech lead from this. Okay, so it has written both the messages to the queue, but I am selectively reading only the second type of message. If you wanted to read personal message, then you would have modified this as 3 here, and you say it is type 3 and display that. Again I have to compile because the code has changed. / receiver. Okay, so it's saying personal message, hi Ajay, how are you? Only thing is in the receiver this type 3 should type 3 only, correct. It is type 3. The personal message is type 3. In the earlier thing it was type 2. Okay, so as you can see, we can selectively receive whichever message you want from the message queue. Is the concept of message queue clear to you?
So that message sent and message received, those are the system calls.
Yeah, all are system calls only. Okay, see, I will show you once again. Yeah, this message send is also system call.
Message get also.
Message get also.
And we are defining that message type, right? Or it's a inbuilt thing or
No. This is a standard message structure that you have to use. First should be of type long, and the name should be message type like this only, and character text, or you can use any other names here. Name is not a problem. First one should be of type long, second should be of char. Okay.
When they're using message queue, this is standard format.
Yeah. In this format only you should send and receive.
Okay. What options we have set like IPC create? Any other useful options we should know about?
Pardon?
Message get is a call which is creating a process here.
Yeah.
So like that, IPC underscore create. Is there any other calls which we should be aware of?
I mean, this is only the thing that to create you have to specify this. If it already exists, you don't have to do this. That is what I am doing in the receiver.
That's correct, sir. For creating a process, this one. Similarly, like this, any other calls are there which we should be aware of is what I'm asking.
No. In message queue is only message get. Okay. Yeah.
Okay.
Now, next one is shared memory. Now, one problem with this earlier IPCs is that the data is getting stored in the kernel, and you have to do lot of context switch here. Okay, so data get into kernel, and from kernel you are reading into user space. So this is taking a lot of time. So what they thought is why not do away with this, so that faster communication can take place, and that is done through shared memory. So shared memory, the object is in the kernel, but it is memory is allocated in the user space, and it is tracked by the kernel as to who is writing to the shared memory and who is reading from the shared memory, how much memory is allocated. All that will be tracked by the kernel. But when a read write is happening, it is happening in the user space. So shared memory is much faster than your earlier two IPC mechanisms. Right?
So message has a different memory allocations.
Pardon?
Message queue has different memories
Yeah.
used by.
See, message queue, the memory allocated is in the kernel space. This is the
Okay,
kernel
but both
space.
the processes will share the same memory space here, right?
Same memory space they are sharing here.
Okay, okay,
In the user space, this is all user space. I have written it here, user space.
okay.
So no context switch is happening. Only when you create the shared memory, the context switch will happen. Once the memory is, there is one more step called a memory mapping. After mapping, the memory is allocated in the user space, and then the processes are free to communicate with each other. Okay, so that part also I have here. So shared memory, yeah, shared.c. Now what I've done here is I'm not using related processes just to keep it simple. I'm using I am not using unrelated process. I'm using related process like parent and child. Suppose the parent and child want to communicate using shared memory. In that case, how do I create a shared memory? Now shared memory, you have to give a name. So normally you give some name like slash basic shm, or you can give any name, and how much memory you want to allocate, like 128 bytes or 256, whatever, 512 bytes. First thing is you have to use shared memory open, where you give the shared memory name o create. So here then o read write. So the IPC will be created and user will be given read write access. And this is again 0666 indicates that read write permissions are given to all the category of users. Now there is one small step that you need to do, that the shared memory size has to be set to some value. Otherwise, when you say shared memory open, the shared memory size will be 0 and further steps will not work. So you have to use f truncate fd shared memory size. So initial size will be set to 512, and then you have to do the mapping. This is where the memory is allocated in the user space. mmap is a API which will allocate memory in the user space and associate that with the shared memory FD. Here FD stands for file descriptor. So every IPC usually will have a descriptor. Like in pipe we had FD, that was a descriptor indicating that where exactly is the shared memory or pipe is in the kernel. Using that variable value you can locate it. So here what I am doing is I am mapping the memory. So total size is 256, and then protocol read write, then mapped shared and use FD. Some arguments are there. So the details of how actually this works, you can find it from ChatGPT, that give me the mmap API details. It will tell you what exactly these arguments are. For now, you know that you will be get a character pointer to the shared memory. So once you get the shared memory pointer, you can write to that or read from it. So here I am going to create a child process. In the child process, I am going only to read it. Okay, so reading is just printing it. I am not using any read function here, just shared, because this pointer only is pointing to that memory. It will sleep for some time so that parent can continue. First it will write and then the child can read from it. So you copy what you want to write to the shared memory. So shared comma hello from shared memory. This is the message I am copying to this, and the parent is going to copy that. You just have to copy. You don't have to use write or read something like that. The parent wrote the message. The moment you copy it to the shared memory, it is just written to that shared memory space, and the child will read. Allow the child to read, and then you can close the shared memory. So shared memory unlink has to be done to clean up the resources which are allocated during the shared memory allocation. So this is again a simple program. Of course, the syntax is far more involved. So you just have to compile this, and you have to run only one program, because within the same program we have communication happening. So parent wrote some message and child reads hello from shared memory. So as you can see, so quickly it will write and it will read from the shared resource. Okay, so this is the third mechanism, and it is one among the fastest. So if whenever speed is the criteria, then you always use shared memory. Okay. Now there is another kind of inter-process communication, not actually to send and receive message, but to synchronize two processes which are competing for a common resource. So let us say we have a printer and two processes want to print. So if both print on the same printer, what will happen? Right? The content of two processes will be mixed up. So you don't want that to happen. So there should be a mechanism whereby I indicate that printer is free now. Okay, and once it is printing the data from process 1, second process has to go in the wait mode. So how do they synchronize the processes? So here what happens is there is a concept of a semaphore. Semaphore is nothing but a variable which has values. If it is a binary semaphore, it has only two values, 0 and 1, whether the resource is available or not available. However, semaphore can have many values depending on how many instances of the resources are available. For example, you have 3 printers, then the semaphore value will be 3. Okay. So here, assuming that there is only one printer, initial value is 1. It means the printer is available. The moment, let's say the parent process will want to use the printer, then it has to acquire it by setting the value to 0. So moment parent makes it 0, other processes have to wait till it becomes 1 again. So when it is acquired the printer, it is unavailable. Okay, so initial value 0 or acquired value 0, it's not available. Now after printing is complete, it has to explicitly release the resource by setting the value to 1. So again the state will come back to 1 here, so that other processes which are waiting for the resource can make use of it. Okay, so here I have used a semaphore program just to give an idea as to how it looks like. So here again you have to create a semaphore. Sem open, you have to give a name like shared memory, ready semaphore, and O create 666 and 0 here. It is 0 because it will be used by the parent first. So you create a process using fork. In the child you are waiting for parent to complete. So what parent does is, parent process is the consumer. So parent waiting for child to finish. Okay, he is doing the other way around. So he wants the child to continue first. So child is doing some work. The semaphore is available. It will sleep for some time. It means it is simulation of some work. Like you give a large print command here, so that the printer is printing something. After the printing is over, after 3 second sleep time, the child says my work is done, and it has to use sem post sem. This is a signal to the parent that I am done with printing, so it can use the semaphore further, and it has to close its semaphore instance and exit. Whereas parent, once it in its space, it has to wait for the semaphore to become free. So sem wait is the API. So it will block until the child signals that it is done with printing, and then once it comes out of it, it says parent is done and it will close. Okay, so this is a another program of inter-process communication. So if I compile this, so child is doing some work, so work done, signal parent, and once the parent receives a signal, it continues. So a proper synchronization happens between the parent and the child. It is not that it can be done only within parent and child. You can have two unrelated processes, like in the earlier case I showed producer and consumer. So both can coordinate among themselves to synchronize and do the work properly in a proper sequence. Okay, so these are the three important inter-process communication. So sometimes if you want to compare these things, how do they compare? Okay, so pipe, message queue, shared memory, and semaphore. So what it is for, like pipe, message queue are for data transfer, even for shared memory it is for data transfer or data sharing, whereas semaphore is for signaling. Okay, it is for process synchronization basically. We will see this usage of semaphore when we want to synchronize the threads. Okay, now what is the type of data that you are exchanging? So in pipe it is byte stream. As you write the data, it will go as a stream of bytes. Whereas in message queue it is messages. Like I showed you, you have to use a struct message and give a ID and the text. Similarly, shared memory, it's a memory space where you write something. It can be again string or integer or whatever kind of data that is possible. Semaphore, this data form is not applicable because this is not for exchanging data. Now kernel involvement. So every read write will happen in kernel, every send receive will happen in kernel for message queue. For shared memory, only while setting up the shared memory, kernel interaction will come. Subsequently, it is in the user space. Okay, and only APIs which execute in kernel space in semaphore are wait and signal. Okay, so that is another thing to note. Now speed, if you see, pipe is medium, message queue is medium to slow, shared memory is the fastest, and semaphore is also pretty fast. Okay, so other things you can just look at, like blocking behavior and random access and all. So data cannot be randomly accessed in message queue or pipes, whereas in shared memory you can randomly access wherever it is. Blocking behavior means once you write, whether the process gets blocked or not. So both for pipes and message queues the blocking happens, whereas for shared memory no blocking happens. Similarly for semaphore the blocking happens, okay, until you signal to the other process that something is done. Okay, so what we have seen today is the four important inter-process communication mechanisms which are widely used, and as a learner of Unix operating system you should be conversant with these terminologies. Okay, pipe, message queue, shared memory, and semaphore. Of course, there is one more last inter-process communication mechanism which is far more involved, that is called as socket. Now all these inter-process communication, what we saw, four mechanisms, they will allow you to communicate only within the machine. The processes have to be in the same machine. If you want to communicate across machine, then you must use sockets because the TCP/IP protocol comes in here. Okay, so socket is for inter-process communication for processes between or processes across machines. I mean, more than one machine can communicate with each other. Process 1 can exist in machine 1 and process 2 can exist in machine 2, and if they want to communicate over a network, maybe local area network or wide area network, they have to make use of socket. So at the end of our the entire session, I have dedicated one topic on sockets only. What sockets are, how to create a socket, which is nothing but a endpoint for communication, how to set its parameter, how to specify what type of communication we want to explicitly specify. All that we shall see subsequently. Okay, these concepts are clear now. Hello.
Yes, sir.
Okay. Now, uh, only I mentioned to you about semaphores, that semaphores are widely used for process synchronization or thread synchronization. Now, how do I create threads in uh, Unix? We have already seen this in C++, but it is interesting to know how threads are created in Unix. If you recall, threads are lightweight processes. That is, if you have a process, this is a process, and every process will have only one path of execution. But suppose within the same process, if we want to implement two execution paths like this, I want to split this execution path into two. This is one execution path, this is another execution path. So we call these as threads. This is thread 1, this is thread 2, and this is the main thread. So this will be executing some code which is independent of the code here and also the code here. But this is the process which will actually create these two execution paths. In fact, you are free to create any number of execution paths. There can be one more thread, thread 3. See that it is within this boundary. Now, advantage of using thread is that there is no switching from or crossing the process boundaries. Okay, if you had two processes, then CPU has to switch between this process and this process whenever uh, two processes are proceeding concurrently. This switching takes a lot of time, whereas if you have threads which are within the same process, there is no context switch, and hence threads are called as lightweight processes. Why lightweight? Because there is no overhead involved in switching from process P1 to process P2, because the address space of P2 is very different from address space of P1. Okay, let us say this is starting from address 8000, this is some 9000. So the CPU has to load all these things, run it, and again unload it, then again load this part, execute, again come back. So this is a lot of overhead associated with uh, context switch between the processes. If it is within the same process, there is no such thing. The same address space will be there, and the two thread can proceed the execution concurrently. Okay, so before we close today, I'll show you a small program how to create a thread in Unix and see how it works. So here we have yeah, process thread this. So what you have to do is you have to use a system called as pthread create. Again you have to use a variable here pthread t, which is defined in unistd.h or in pthread.h. Now one thing is very confusing in Unix is which header file contains which data type descriptions. So that has to be remembered all the time, but today we have ChatGPT, which if you ask, it will tell you which header files to use for which variables. So whenever you are creating threads, you declare a variable of type pthread_t, which goes as the first argument. In fact, you will pass its address here. And threads will have many properties. That is, whether thread should have some priority assigned, or thread should terminate after the completion, or it will get blocked. So all those things have to be mentioned as another structure here. If you put null, by default it will not wait for the things to execute, it will proceed immediately. And what function to run in the thread process space. So since I am creating only one thread, I want this program to run, that is this function to run. The functions with this syntax only. The return time should be a generic pointer. You can give any name, one thread or f1, anything. And the argument should be again of generic type, white star. And here you say what the thread will do. I am a new thread. Okay, that is the message it is displaying, and it is returning null. It means it is not returning any pointer to any other function, just null like that. So once you create a thread, to run the thread you just have to say pthread join and use this variable pt here, and again second part as null. So this is the main process which has created only one thread now, and once the function runs in the thread, in the second thread, it will come back to this point, and then you can say back in main thread. Okay, if you wanted to create one more thread, again pthread create ampersand pt1 null fun thread 1, like that. So two threads will be running along with the main thread. So I'm not doing that, we shall see that next time. But just for completeness, let us see how to compile this. So as you can see, I am new thread and back in main thread. So main thread is running and it is waiting till the child completes. So that is why the child executes first. I mean the thread process will run and then the main will resume. So the function which you declared at the beginning of the program, that got executed, and then the main will complete the remaining part of the program and close. Okay, so threads are very lightweight and extensively used while building many applications. Like for example, you want to build a web server, so it is more sensible to build a web server with threads, so that every client which connects will be handled by a new thread, and once the service is done, the thread can close. So many threads will be running, and since switching is not there, the processing will be pretty fast. Okay, so we shall resume our discussion on threads, how to create more than one thread, how to synchronize all that in our next session. All right. Okay.
Yes, sir.
Yeah, I'm closing.